right. All right, hi everyone. We are excited to present MapEx, an indoor exploration framework that uses this probabilistic information gain from predicted global maps. So here we have an indoor, a promoter exploring an indoor environment. It needs to decide, should it go into a room to the left, go directly down the hallway, or to the right to another hallway to maximize environmental understanding. So let's take this simplified problem. Between these two frontiers, where should the robot decide to go to gather high-value information? And as much of the indoor environment is included, there has been a lot of really exciting work that has been leveraging map prediction to predict maps in the unknown space for better exploration. Like so, here are some example predictions from our own work, where it is very exciting because we can often also be able to predict very close to ground truth when we have enough context about the area. However, a key limitation is that by relying on these predicted maps, they can be inaccurate. And one way may be to use uncertainty as a heuristic. However, let's say for these two frontiers, it has a similar amount of nearby uncertainties. But visiting these two can lead to dramatically different information gain. Specifically, visiting these two sees very different amount of areas. Hence, we also need to reason on coverage. Therefore, we present MapEx, which is exploring by predicting maps and jointly reasoning over what the robot can observe, hence coverage, and its uncertainty.
So now I'll go over the details of the MapEx framework. It's composed of two main components, predicting maps from observations and using map predictions for exploration planning. So how does the robot reason beyond the observed area? Prior work has generated local predictions, but in this work we aim to generate global map predictions instead to enable longer horizon planning. The key idea is that we use an image embedding network. Image embedding network fills in occluded or missing regions and completes the image by in-painting it. We use this technique in the context of indoor map predictions. So given the observed map, the Llama network, which is fine-tuned with floor plan dataset, can generate plausible map predictions, and this is comparable with the ground truths. One caveat is that map predictions can still be incorrect. As a solutions, we generate multiple predictions from ensemble networks, which is fine-tuned with the different training sets. We also model the uncertainty as a variance of predictions, and we maintain the pixel loss variance map as uncertainty map. We also maintain a mean predict map, which is on average predictions. So this was the first part of the framework. But the next question is, how do we actually use such predictions for better exploration planning? So it boils down to how to score each frontier, or how to estimate the information gain at each frontier. When there's no predictions, when there's only observed map, the way how we can get information gain or sensor coverage is to generate virtual raycast, but it often overestimates the information gain. Why do we just use the raycast on the predicted maps? Well, it's susceptible to wrong predictions and often underestimates the information gain. So our solution is to employ probabilistic raycast on predicted maps. Each ray starts at with a value of 0 and accumulates occupancy values as it passes through the predicted maps until it reaches a stopping threshold. By using probabilistic raycast, we can generate a visibility mask that better estimates the information gain or potential sensor coverage. After this, we sum up the values of the uncertainty maps within the visibility mask. In doing so, the MapEx can jointly reason on both potential sensor coverage as well as uncertainty. For the experiments, we used a simulator based on the KTH datasets. For baselines, we compared with the UPenn and injector. And for metrics, we measured coverage, predicted IOU, and topological understanding. Qualitatively speaking, MapEx considers both uncertainty and potential sensor coverage. Sometimes it prioritizes visiting areas that yield more potential sensor coverage, while sometimes robot prioritizes visiting more uncertain areas. We also compared the behavior with other baselines. While UPenn optimizes for reducing uncertainty and iJector aims to maximize sensor coverage, MapEx considers both sensor coverage as well as uncertainty, yielding to the best results. And quantitative results also show that our MapEx framework outperforms the baseline in all metrics.
Yeah, so we've been really excited to build upon MapEx to empower new frontiers. Specifically, we've been leveraging our information gain heuristic in a more pathwise manner in Pipeliner with some exciting results. And we've also been digging deeper into how humans explore by looking at user studies and also leveraging these insights to build an RL framework. So please check out these two extensions of our work. So in conclusion, we present MapEx, which is the key insight is to explore by predicting maps and jointly reason over what the robot can observe and its uncertainty. Please check out our poster here and also our QR code where you can predict your own maps and explore. And I want to leave us with some generalizable insight, since maybe not all of us here are working on this exact problem. So if you're leveraging uncertainty, I think it is a very powerful heuristic. We've put a lot of thought on also quantifying how much uncertainty we can resolve by looking at sensor coverage. And if you're working on problems where you're exploring big areas, we found it very helpful to really think long horizon by predicting global maps and also simplifying the problem